In this video, we're going to discuss the gradient vector and the directional derivative. First, I would like to start with talking about the phrase directional derivative to see that we understand what that means. If you think back to Calculus 1, you did derivatives on functions of a single variable, which means that you found the rate of change of the height of a function as you move from left to right. But really, we only had one direction to go when we thought about functions of a single variable. If we consider a function of two variables, this really represents a surface in 3 dimensions. So now if we are at a given point and we want to find a derivative, we really need to ask ourselves, well, which direction are we going in? Because depending on what the function looks like, the rate of change will be different depending on which direction we go from any given point. So this is what we want to try to solve. We want to be able to know what the derivative is no matter which direction we pick. So I'm actually going to skip ahead slightly to this here. This tells us our formula for the directional derivative, and that is what we call a gradient vector here, dotted with the vector u, the unit vector u, which tells us the direction that we wish to go. We'll have a similar definition of a directional derivative for a function on 3 independent variables. All right, so we had this piece here that we called the gradient vector. So I'm going to go ahead and define that now, and that's what's in these first 2 lines. The gradient vector on a function, a differentiable function of 2 variables, is the partial derivative of f with respect to our first variable, x here, and that goes into the first coordinate, and the partial derivative of f with respect to the second variable, which is y here, that goes into our second coordinate. And we have a similar definition for the gradient of a 3 variable function. All right, so f sub x in the first one, the partial of f with respect to y in the second coordinate, and the partial of f with respect to z in the third coordinate. And that's really it. So let's go ahead and do an example. So we're going to let f of x, y, this 2 variable function, be e to the x cosine of y. Part A is going to ask us to find the gradient of f at 0, 0. So the first thing you want to do is find f sub x, or the partial of f with respect to x. And this is e to the x cosine of y. Then we want to find the partial derivative of f with respect to y. And this is negative e to the x times sine of y. And that will be f sub x and f sub y. So our gradient vector then is the vector e to the x cosine of y in the first coordinate, and then negative e to the x sine of y in the second coordinate. Okay, so then the gradient of f of x comma y evaluated at, the gradient of f evaluated at 0, 0 is the vector. All right, this is e to the 0 times cosine of 0. Cosine of 0 is 1. E to the 0 is 1, so this is 1. And then we get negative e to the 0th power, which is negative 1, but this is all multiplied by sine of 0, which is 0. So this is 1, 0. So we get the gradient of f evaluated as 0, 0 is the vector 1, 0. Again, remember that the gradient results in a vector. All right. Then part B here says to find the directional derivative of f at the point 0, 0 in the direction of the vector I plus root 3j. The first thing we want to do is we want to convert this vector into a unit vector in that same direction, because our formula has to do with a unit vector u. So let's make sure that that is a unit vector. Well, how do we do that? We can calculate the magnitude of that vector. So this is the square root of 1 squared plus root 3 squared. This is the square root of 4, which is equal to 2. So this tells us that the length of that vector is 2. So our unit vector is 1/2 times 1 comma root 3. Or in other words, 1/2 comma root 3 over 2. And so this is the unit vector that points in the same direction as that vector in part B. So our directional derivative is d sub u of f is equal to 1 comma 0, our gradient vector evaluated as 0 comma 0, dotted with u, which is 1/2 comma root 3 over 2, which is all equal to 1/2. All right. That's it for that one. Let's do C real quick. Again, we want to find the unit vector in the direction of 3 comma 4. Well, this is to get the magnitude. Oops. We do our distance formula, and this is 5. So the vector, the unit vector u, is 3/5 comma 4/5. And then our directional derivative is the gradient of f, which was 1 comma 0, dotted with this vector, this unit vector u. Oop, that's supposed to be a 5. And we get 3/5. And that's it for that problem. We'll do one more example here in this video. So we got a similar thing, but a 3-dimensional vector here. Let's find the gradient of f. So first off, f sub x is equal to, let's see, y squared e to the xyz times yz. F sub y is equal to y squared times the derivative of e to the xy, which is e to the xyz, which is e to the xyz times xz plus 2y e to the xyz. All right, we had to do our product rule there because y squared is a function of y and e to the xy was a function of y. And then we have f sub z is equal to y squared e to the xyz times xy. And you'll want to write those down, and we can use that on this next part. Y squared times e to the xyz times xz by e to the xyz. It's all right, just writing down these values. All right. And so the gradient of f at 0, comma 1, comma negative 1. Gradient of f at 0, 1, negative 1 is equal to, now we plug in 0, 1, and negative 1 into f sub x. We get 1 times e to the 0, which is 1 times negative 1. So this is negative 1. And then we get 0, comma 1, comma negative 1 of value are plugged into the y squared times e to the xyz times xz plus 2y e to the xyz. Since x is 0, that first term goes to 0. The second term is 2 times 1 times e to the 0, but e to the 0 is 1, so this is 2 times 1, which is 2. And then we plug all of that into the 0, 1, and negative 1 into f sub z, partial derivative of f with respect to z. And we end up multiplying by x at some point. So since x is 0, that's just all 0. And that's part A. All right. So for part B, we'll want to find a unit vector in the direction of 3, 4, 12. So this is the square root of 3 squared plus 4 squared plus 12 squared. This is 25 plus 144. It's the square root of 169, which is equal to 13. This tells us u is equal to 3 over 13, comma 4 thirteenths, comma 12 thirteenths. And that's our unit vector in the direction of the vector 3, comma 4, comma 12. And then so the directional derivative is evaluated at 0, 1, negative 1 is this vector negative 1 to 0 dotted with that vector we just found, which was 3 over 13, 4 over 13, 12 over 13. And this dot product is negative 3 thirteenths plus 8 thirteenths plus 0 thirteenths is equal to 5 thirteenths. Go ahead and practice on your own and find part C. Again, what you'll want to do there is you'll want to find the unit vector in the direction of the vector 1, 1, 1, and then you take that with the dot product of that with this directional this gradient that we found, and that will tell you the directional derivative, and that will complete this video.